Let's see further examples related to PDAs. Let's now see actually an example from the opposite direction. The previous example was given a language description. How can we design a PDA that recognizes it? Let's now try to do something in the opposite direction. We will be given a PDA and we will try to describe the language that it recognizes. So given the following PDA is Q0, the first transition is epsilon dollar, goes to some state Q1, which has a loop 0 epsilon and A, and 1 and epsilon and A, and another transition 0 epsilon and A goes to Q2, which has also a loop A, 0 and A and epsilon, and 1 A epsilon, and it has a final transition epsilon dollar epsilon, and goes to an accepting state Q3. So given such a PDA, we want to describe the language it recognizes. Let's try to see if we can find a description for the strings that are accepted by this machine. So we can see that starting at Q0, the first thing that the machine does is push the special delimiter dollar on the stack. This is so that the machine at the end can recognize at any point, for that matter, at any point can recognize that the stack becomes empty or not. Because if at any point while popping from the stack, if the machine pops a dollar, it will know that the stack at that state at that time is empty. So this is just the usual dollar delimiter pushed at the beginning. Let's see what happens for the rest of the states. It seems like at stage Q1, the machine, while reading input 0 or 1, it doesn't matter which one, it doesn't pop anything, it doesn't remove anything from the stack. It pushes a single symbol A on the stack. So for every symbol that it has read at the beginning, through this loop, it just reads the symbols, and whatever the symbol is read, a corresponding symbol is pushed on the stack. So all these symbols, let's say it has read 5 symbols, so dollar, 1, 2, 3, 4, and 5 A's are pushed on the stack. The rest of the stack is empty. If it has consumed the first part of the string through these loop transitions. But there seems to be yet another possible outgoing transition from Q1. When it sees a 0, it has another possible outgoing transition at any point. So if it can take this transition while seeing zeros as well, but at the same time make a non-deterministic guess and take this branch. If it takes this branch, let's say it has taken that branch, once it has reached this point and now it sees a 0 and it takes this transition. If that's the case, what it does afterwards, while reading 0, it hasn't done anything on the stack because it hasn't popped or it hasn't pushed a new symbol. For the rest, what it does is takes this looping transition, reading any symbol 0 or 1 from the input. So for the rest, whatever the symbols are, it just reads the input symbol and pops a symbol A from the stack, reads a symbol from the input and pops an A from the stack. So it keeps on reading a symbol from the input and pops, basically removes a symbol from the stack. Until when? until it can take this transition, and it can take this transition only after popping all the A's that are previously stored through these transitions that are previously stored on the stack. So the dollar delimiter will be reached when we consume all the A's that had been stored. So which means that to be able to arrive at our accepting state Q3, it should be the case that through these transitions we must completely empty the stack, which was filled through these transitions, completely empty the stack through these transitions, and also finish processing the whole input string, okay? So that we arrive at Q3 and the stack becomes empty. This implies that however many characters or symbols are processed through this looping transition at Q1, their number should be the same as the number of symbols that are processed through the looping transitions at Q2, so that we can have an empty stack that only consists of dollar at the end of these transitions at Q2, because this part is simply storing A's corresponding to every input symbol that is read. This transition at Q2 is simply removing every symbol that was stored previously on the stack until it arrives at dollar at the special empty stack delimiter, okay? And once we arrive at Q3, if these numbers are the same, then the string is accepted and we are at state Q3. So now we can give a description. It should be the case that if we have K symbols in here at the beginning, we should have K symbols in the string at the end. Basically, you should realize that we don't actually check any of the symbols, because either if we consume a 0 in the string or a 1, we are pushing the same symbol A on the stack. And in here, while consuming the symbols at Q2, it's the same. Whichever symbol we read, either 0 or 1, we pop the same symbol A from the stack. So what the specific symbols are in here doesn't matter. It seems like only their count matters. However many symbols we have stored in our stack through these transitions, we expect them to be the same as the symbols that we pop through these transitions, so that at the end we can arrive at the empty stack condition and have no remaining input symbols to be processed. So we go to the accepting state. Note that this 0 transition in here corresponds to having this middle symbol to be 0. So now we can describe the language as L equals W in 0, 1 star, such that, because our string consists of zeros and ones, A is just a stack symbol, not a symbol in our input alphabet, such that length of W is equal to 2k for some integer, for k greater than or equal to, let's say, 2k plus 1. The length should be odd because we have k in here, and an extra 0 in the middle. So the length should be odd. It should be 2k plus 1 for k greater than or equal to 0. And what this middle symbol is also important, it seems. For instance, if that middle symbol was a 1, we couldn't take this transition to arrive at Q3. So this means that in the string, the middle symbol should be a 0, and middle of W is a 0. Okay, so this description provides the description of the language that is recognized by this PDA. Let's see yet another example. For this one, let's try to design a PDA for a given language. So given the following language description, L consists of let's say x to the reverse, such that x is in 0, 1 star. What types of strings will be in this language? We should be able to divide the string into two equal halves, such that the second half is the reverse of the first half. So for instance, 0, 1, 1 and 1, 1, 0 belongs to the language. Why? Because we can split the string into two equal halves, so that the second half, 1, 1, 0, is the reverse of the first half. The reverse means reading the string from right to left. If I read the first half of the string from right to left, I have 1, 1, 0, which is the second half of the string. So this string belongs to the language. Now what we want to do is we want to design a PDA that recognizes this language L, which means that it should accept all such strings belonging to this language, and it should reject all strings that do not belong to it. Let's first try to think of the main idea while designing this PDA. The idea will be as follows: main idea, or the informal description of the PDA that we want to design. What we want to do is, so given such a string, we want to be able to store exactly the first half of the string in the stack which we have available for our PDA. So once we get to the middle of the string, we have in our stack, if we can have 0 and 1 and 1, once we get to the middle, if we have our stack in this configuration, then for the rest of the input string, we can simply compare every symbol, read every symbol 1, and try to see whether the top of the stack symbol matches that one. If it does, remove it. Next one, try to see if it matches. 0, try to see if it matches. Because if this is x, if the first half is x, while processing all these symbols in x, if we store them in our stack, remember that the stack works with the LIFO principle, which means that this string x will be actually stored in the stack in reverse order, which is exactly the order that we want to be able to compare the second half of the string. Okay, so what we will do is basically, but a second point remains is, how do we know that we have reached the half of the string so that we can compare the rest of the string against the string that we have in the stack? Well, that's also easy with the PDAs, especially that the PDAs are inherently non-deterministic, which means that at every time that we do a processing of the input string, we can make a non-deterministic guess that that we have reached to the middle of the string, so that for the rest we will simply compare the remaining part of the string against the stack. So we will be doing two things at the same time. So store the first half of the input string in the stack. How can we do this? For every, let's say, symbol A in input, push A, that symbol, into the stack. This is what we do. We keep on repeating this operation. Whatever symbol you see, you simply push it on the stack. Whatever symbol you see, you push it on the stack. We repeatedly do this until we reach the middle of the string. and the middle of the string, we can make a non-deterministic guess about it. At the same time, basically non-deterministically guess that middle of the string is reached, What do we do if we reach at the middle of the string? We should be basically now comparing the remaining part of the string against the string that we have stored so far in the stack. Compare. So this is one main operation. Then at the same time we should be repeatedly comparing. So compare rest of input string against string stored in stack. More specifically, how can we do this? For every symbol A that we read from the input, we try to pop the same symbol from the stack. For every A in input, pop A from stack. So if I have guessed that this is the middle of the string, if our machine has guessed that this is the middle of the string, if it reads a 1, it tries to pop or remove a 1 from the stack. If it reads another 1, it tries to pop or remove another 1. If it reads a 0, it will try to pop yet another 0 from the stack, and at the end the stack will be empty. So we should be able to repeatedly do all these removals if the first half of the string is stored in reverse order in the stack, and we don't do anything extra to store X, the first half of the string, in reverse order, because the stack itself works with the LIFO principle, meaning that the last element that you insert in the stack will actually be at the top of the stack anyways. Okay, so this is our informal description of the PDA. Let's now formally show the PDA with a state transition diagram. Our initial starting state Q0. To be able to discover that the stack becomes empty, our transition epsilon $, that only pushes the special delimiter $, into the stack, Q1. Okay, at Q1 we will implement this operation. We will repeatedly, basically, for every symbol that we read from the input, we will push the corresponding symbol into the stack repeatedly. So at Q1 we have a loop that repeats, where if we read, let's say if we read a 0 from the input, we don't pop anything from the stack, we push a corresponding 0 into the stack. Same for the symbol 1, don't pop anything from the stack, push a symbol 1 into the stack. So this looping transition actually implements the first half, basically assuming that we are still reading symbols from the first half of the string. We will keep on storing whatever symbols we see in our stack, but at the same time, so to implement this statement at the same time, we make a guess, a non-deterministic guess, epsilon. So while doing these storings, at the same time, for every symbol that you have reached, make the guess that you have reached to the middle of the string, and go on now to implement the second half of our idea, which is now assuming that you have reached to the middle of the string. Now keep on reading symbols from the input and removing the exact corresponding symbols from the stack. At Q2, basically, if you read a 0 from the input, now pop exactly the same symbol 0 from the stack and don't push anything. read a 1 from the input and pop exactly the same symbol 1 from the stack. So basically with this loop, we are actually comparing the second half of the string against whatever we have in the stack, which was stored within this loop. And at the end, if upon finishing the whole input string, the processing of the input string, and we have arrived at the end of the string, epsilon basically for the input symbol, if the string, the stack becomes empty, which means that we have been able to verify that every element that is stored in the stack corresponds to every element in the first half of the string, stored in reverse order, then go to the accepting state, Q3. So this is our PDA that recognizes the given language L. Let's see yet another example.